Hello students, having seen the very important cases of conduction heat transfer through the single slab and the composite slab also, along with the convection on both sides of the composite slab. Now let me introduce the another important case of radial conduction heat transfer through a hollow cylinder. Okay, this is an entirely different case as compared to the previous cases I have discussed. Let me introduce the next case called as the radial conduction heat transfer. Radial conduction heat transfer through a hollow cylinder. Radial conduction heat transfer through a hollow cylinder. I would like to show the exact geometric configuration of this case. I have considered a hollow cylinder. Inside this hollowness, maybe some hot fluid is there. There is hollowness here. Inside this hollowness, there is some hot fluid may be there. Some hot gases may be there. This is the hollow cylinder, a solid material here. This is all hollowness. The inside radius of the hollow cylinder is R1 and the outside radius of the hollow cylinder is R2. This is R2. L is the length of the hollow cylinder and K is the thermal conductivity of the hollow cylinder. K is the thermal conductivity of the hollow cylinder and R1 is the inside radius and R2 is the outside radius. This is all the solid material of the hollow cylinder. Conductivity is K. The inside surface of that hollow cylinder may be maintained at a temperature of T1 degrees Celsius. The inside surface, all this inside surface is maintained at a temperature of T1. The outside surface of the hollow cylinder is maintained at a temperature of T2. T1 is greater than T2. T1 is greater than T2. L is the length of the cylinder. Now, because there are temperature gradients existing along the radial direction, because at a different radius we have a different temperatures. Temperature is a function of R. Temperature varies radially. Temperature is varying radially in this direction, not axially. Temperature is only a function of R. In this direction, temperature gradients are existing. Because there are temperature gradients existing along the radial direction, heat must be conducting along the radial direction. According to the Fourier's law of conduction, the direction of the heat flow is always the direction in which the temperature is decreasing. There is a temperature gradients existing along the radial direction. Therefore, heat must be conducting radially outwards along this direction. These arrows indicate the direction of the radial conduction heat transfer occurring. L is the length of the cylinder, K is the thermal conductivity of the material. I would like to write that point here. Since temperature gradients are existing, along the radial direction, heat must conduct radially outwards from the inner surface at T1 to outer surface at T2. Heat must be conducting radially outwards along this radial direction. Okay. We are given the two boundary conditions of the temperature at R is equal to R1, T is T1, at R is equal to R2, T is T2, temperature is T2, T1 is greater than T2. See, I am proposing one very important assumption that steady state heat transfer conditions are prevailing. Earlier also I have told you very clearly that whenever there is heat transfer is happening and whenever you are proposing the steady state conditions, there must be a source of heat and there must be the sink. Without source and sink, we can never expect to maintain the steady state heat transfer situation. Source means there must be something that is generating heat, some other form of energy, maybe electrical form or a chemical form or nuclear form. Any other form of energy is getting converted into the heat energy. That kind of a source I am assuming inside this hollow cylinder, this hollowness, there is a source of heat which is generating heat or producing heat, and this side there is a sink. Here heat is being generated maybe by the combustion of the fuel or maybe nuclear reaction, or I can keep some electrical power coil here which is generating heat, and the sink is always there in the form of the atmosphere which is able to receive the heat. The most common sink what we can propose in the heat transfer problems is atmosphere. Atmosphere is always there. Okay. So, because there are temperature gradients are existing along the radial direction, heat is conducting radially outwards. This temperature, all this along this inside surface, the temperature is maintained as T1, and outside surface, all along the outside surface, the temperature is maintained as T2. T1 is greater than T2. So, assume steady state. Steady state means what? Temperature at a particular location inside the body must not change with respect to the time. Steady state means temperature at any given spot or at any given location must not, should not vary with respect to the time. Best example I told you already, our human body is at steady state temperature of 37 degrees Celsius. Assume steady state, one dimensional, that is radial. One dimensional, that is radial conduction heat transfer. Through hollow cylinder. Assume steady state one dimensional radial conduction heat transfer through hollow cylinder with constant K, obviously with constant K of the material. K is a thermophysical property. Now, the main difference what you can see between the conduction through a slab and radial conduction heat transfer through a hollow cylinder through this geometry, the main difference I am just highlighting here. Earlier case which I have done in case of the slabs, earlier cases, if this is the slab, if the conduction is happening like this, the area of the conduction will not change in the direction of the heat flow, here or a here or a here. Everywhere along the direction of the heat flow, area of the conduction heat transfer remains constant in case of this slab geometry. Now, that is not valid. That kind of things will not happen here. Here in this case, unlike in case of the slabs, here the area of conduction heat transfer changes in the direction of the heat flow. You can see here, we can clearly see that this is the direction of the heat flow. If this is the direction of the heat flow, what is the area of conduction heat transfer here at the inside surface? At the inside surface, the area of conduction heat transfer is 2 pi R1 into L. Look at this. Because this is the direction of the heat flow at the inside surface. At the inside surface, the area of conduction heat transfer is 2 pi R1 into L. At the outside surface, here the area of conduction heat transfer is 2 pi R2 into L. Here it is 2 pi R2 into L. Here it is 2 pi R1 into L. That means in the direction of the heat flow, the area of conduction heat transfer is changing. That is a very most important difference between the conduction through a slab and the radial conduction heat transfer through a hollow cylinder. Okay, the distinguishing very striking difference between the slab, conduction through slab and conduction through a hollow cylinder. And I am going to write that unlike in slab, here the area of conduction heat transfer changes in the direction of heat flow. Okay, that is very important. As you can see here, at the inside surface it is 2 pi R1 into L, and the outside surface here at the outer radius the area of conduction is 2 pi R2 into L, because Fourier law very specifically says that the area of conduction must be perpendicular to the direction of the heat flow. What is the direction of heat flow here? What is the direction of heat flow? This is the direction of heat flow at the inside surface. What is the area perpendicular to the direction of heat flow? At the inside surface it is 2 pi R1 into L. Here at the outer surface it is 2 pi R2 into L. So, unlike in case of the slab, here the area of conduction heat transfer changes in the direction of heat flow at any radius r measured from the axis. All radii are measured from the axis at any radius r. Area of conduction heat transfer is 2 pi RL. At any radius r measured from the axis, area of conduction heat transfer is 2 pi RL. Here I could show it graphically also. If this is the end view of the hollow cylinder, at any radius r arbitrarily selected here, at any radius r measured from the axis, this is the direction of the heat flow. So, this is the direction of the heat flow. So, the area perpendicular to that direction of the heat flow will be 2 pi r into L, right? At any radius r, 2 pi r into L is the area of conduction heat transfer. Because this is these white color arrows indicate the direction of the heat flow. Okay, that white color arrows indicate the direction of the heat flow Q. Q is the rate of heat transfer. This is the direction of the heat flow. The area perpendicular to the direction of heat flow at any radius r measured from the axis, it is 2 pi RL, which is here at the inside surface the area of conduction is 2 pi RL, 2 pi R1L. At the outside surface here the area of the conduction heat transfer is 2 pi R2 into L. So, conduction area is changing because this is the direction of the heat flow. It is changing from inner surface to the outer surface. Writing the Fourier law of conduction, the rate of radial conduction heat transfer minus Ka dt by dr. Q is equal to minus k into 2 pi RL dt by dr. Okay, L is the length of the cylinder. Now the T is a function of R. Now I separate the variables R and T. We get Q into dr by R minus 2 pi KL into dt. Now you could integrate this equation, both sides. But while integrating, I would like to keep the limits of integration so that the constant of integration can be avoided. It need not be written. What are the limits for the R? Inner radius, this is inner radius R1. Okay, outer radius is R2, R1 to R2. What are the respective temperatures? T1 to the T2. Now, this Q should not be a function of R. This Q, rate of radial conduction heat transfer, rate of conduction heat transfer should not be a function of R to satisfy this steady state assumption. To satisfy this steady state assumption, that is, what is the steady state assumption? Temperature should not be a function of R. To satisfy that steady state assumption, this Q should not be a function of R. Same argument, whatever I had given in case of the slabs. This argument I had told you earlier also in case of the slabs. Just similar to conduction through slab, here also, there also I said Q should not be a function of X to satisfy the steady state heat transfer situation. Please recall that when I was deriving the conduction through a slab, I had very clearly mentioned that Qx is Qx plus dx. Qx is Qx plus dx to satisfy the steady state heat transfer conditions. In the similar manner, here also Qr should be equal to the Qr plus dr to satisfy steady state heat transfer conditions. Q should not be a function of R, that is, QR should be equal to the QR plus dr. Why is like that? You can understand like this. Supposing if I would like to explain this statement. Why is like that? I am writing like this. Supposing if you take a small cylindrical element, if you just take a small differential cylindrical element, if you just take it, if you just take a small differential cylindrical element, if you just take this QR and QR plus dr should be equal. QR and QR plus dr should be equal. Okay. Why is like that? That means to satisfy the steady state, that is very important note here. If you assume that there are 100 joules of heat is conducting into that cylindrical element in 1 second, in the same second 100 joules must vacate. If 100 joules are entering, only 90 joules are leaving. Say if they are not equal, what is happening? I am going to explain. Supposing if this is 100 joules are entering in 1 second, there is a rate of heat transfer here is 100 watts. If the rate of heat transfer is something else like 90 watts, say 90 joules per second is the rate of heat transfer here. That means if they are not equal, what will happen? 100 is entering, 90 is leaving. The remaining 10 must stay back within that cylindrical element. That staying back energy will not keep quiet. It keeps increasing the temperature of that cylindrical element from time to time. But steady state assumption says that temperature should not change with respect to the time. That means to satisfy this steady state, this QR should be equal to the QR plus dr. For that matter, this Q should be the same all along the radius. At any radius, if you select, the value of the Q must be the same. Here the value of the Q here and the value of the Q here should have to be equal. Both must be equal to satisfy the steady state. And moreover, there is no heat generation. I already in the assumption also you may write no heat generation. No heat generation anywhere in the cylinder. No heat generation anywhere in the cylinder. In the cylinder, heat generation is not there. So, in the source there is a heat generation, in the sink which is picking up the heat, but in this body there is no heat generation. So, QR is QR plus dr. Now, I have decided that, we have concluded that Q should not be a function of R. Therefore, it can be taken outside the integral. After integration, by putting the limits, you get Q into ln R2 by R1. This K is anyway a constant. Remove the minus, interchange the limits. 2 pi KL into T1 minus T2. Therefore, this is the rate of radial conduction heat transfer through a hollow cylinder. Now, having seen the rate of radial conduction heat transfer through a hollow cylinder, now I would like to introduce the third kind of thermal resistance. Earlier I had given you two thermal resistances. One is B upon Ka. Second thing is 1 upon Ha. So earlier we have discussed about two resistances, B upon Ka and 1 upon Ha. The third resistance of conduction sort, conduction type, I am going to introduce here by taking this as the thermal potential. Delta T is the thermal potential. This is the heat current. Look at this. This is the delta T or thermal potential. This is the heat current. The rest will be the thermal resistance. The corresponding conduction thermal resistance offered by is, this is the thermal circuit. What is the thermal circuit? That is the thermal potential delta T is the thermal potential T1 minus T2. The flowing current is Q. This will be the thermal resistance, the conduction thermal resistance, because it contains K. K speaks of the conduction mode of heat transfer, just like H speaks of the convection mode of heat transfer. Conduction thermal resistance offered by the hollow cylinder will be T1 minus T2 by Q, thermal potential divided by the current. Look at the previous formula we have. What is the T1 minus T2 by Q? Ln R2 by, when the Q go to the denominator, becomes ln R2 by R1 divided by 2 pi KL. So many Kelvin per watt. This is the third resistance which I am putting. K is the conductivity of the material. If we just look at that formula, we can easily notice that if R1 tends to R2, or if R1 tends to R2, that means, that is, if the thickness of the cylinder is very small, if the thickness of cylinder is very small, then R2 by R1 ratio, then R2 by R1 ratio will be tending to 1, right? If the thickness of, look at this, if the thickness of the cylinder is very small, if the thickness of the cylinder, if this is R1 and this is R2, if the thickness is very small, if this thickness, R2 by R1 ratio will be tending to 1. So then the thermal resistance also will be tending to 0. Also, if conductivity of the cylinder, if the conductivity of material of cylinder is very high, if conductivity of material of cylinder is very high, like copper cylinder is very high, like copper cylinder, a thin copper cylinder. For example, a very thin copper cylinder, a very thin copper cylinder offers 0 conduction resistance. Copper has got a very good thermal conductivity, 385 watt per meter Kelvin. A very thin copper cylinder almost offers 0 conduction resistance, almost offers 0 conduction thermal resistance, almost offers 0 conduction thermal resistance. Because this numerator is tending to 0 if the K is very high, the thickness is very small, or if the K is very high, and obviously that this ratio will be tending to the 0. And in fact, in the heat exchanger analysis, we always neglect the conduction thermal resistance offered by that separating wall, because all the heat exchanger pipes are usually made with a very good conducting materials like copper or its alloys. So, in case of the heat exchanger design, in case of the heat exchanger analysis, most of the occasions we will neglect the conduction resistance offered by the separating walls between the hot fluid and cold fluids. Okay, now this is the hollow cylinder case. Now I would like to consider a composite cylinder. Radial conduction heat transfer through a composite cylinder. Composite cylinder means made up of 2 different materials, R1, R2, R3. Composite cylinder means one material is lagged above the other. We can think of like this. Supposing there is a copper pipe. Generally, most of the high pressure fluid carrying pipes are made with metals. Why? Metals are strong enough. They can withstand the high pressures and high temperatures. That is why whenever a fluid, if you want to carry in a pipe, if the pressure of the fluid is high, if the temperature of the fluid is very high, only we have to pass it through a metallic pipes, because metals are strong enough to withstand the high pressures and high temperatures. But unfortunately, metals are very good conductors of heat. So they can't resist the heat flow. Easily heat will be conducting through those materials. I want to arrest that heat flow. For that purpose, maybe that metallic pipe I have lagged with some very good insulating material. A metal pipe is there, and around that a very good insulating material like asbestos material has been lagged, has been packed around that hollow cylinder. So that will become a composite cylinder. Inside material is having one thermal conductivity and outside material has got different thermal conductivity, because conductivity K is a material property. So 2 different materials, one lagged above the other. Okay. Right. Now this is R1, R2, and this is the outermost radius is R3. Now the innermost temperature is T1 and the outermost temperature may be T3. This junction temperature may be T2. Outermost is T3 and innermost is T1 and the junction is T2. So T1 is greater than T2 greater than T3. T2 may be the junction temperatures, because temperature gradients are existing along the radial direction. Heat must be conducting radially outwards. This is the direction of the heat flow. This is the direction of the radial conduction heat transfer. L is the length of the composite cylinder. This is the rate of radial conduction heat transfer Q. Q over T1 is greater than T2 greater than T3. Assume steady state, one-dimensional conduction heat transfer through a composite cylinder. Composite means more than one material. Okay. So, how many thermal resistances you may expect between this innermost temperature T1 and the outermost temperature T2? Between T1 and T3, there will be two conduction resistances kept in series. One, because heat current must pass through the inner material and then it must pass through the outer material. Therefore, the two resistances, whatever you are seeing, they must be in series. Okay. So, if you just look at the thermal circuit for that radial conduction heat transfer, there will be two resistances in series, because unless the heat is conducting through this, heat cannot conduct through this. Okay. The thermal circuit comprises two conduction resistances T1, T2, T3. The first resistance will be ln R2 by R1 divided by 2 pi K1L. The second resistance will be ln R3 by R2 divided by 2 pi K2L. Look at this, both are conduction resistances. I am writing the first resistance is ln R2 by R1 divided by 2 pi K1L. When you come to the conduction resistance offered by the outer material, ln R3 by R2 divided by 2 pi K2L. ln R3 by R2 divided by 2 pi K2L. This is the conduction resistance offered by the outer pipe material. This is the conduction resistance offered by the inner pipe material. Two resistances are in series. So, that is the thermal circuit for the heat transfer occurring between the innermost surface and the outermost surface T1 and T3. Therefore, rate of radial conduction heat transfer T1 minus T3 divided by sum of the two resistances. They are in series, we can simply add up the two resistances. So many watts. This is the rate of radial conduction heat transfer through this composite cylinder. And which resistance will be more? If there are two resistances there, which will be more as compared to the other? That will be decided based upon the what is the relative magnitudes of the conductivities and the thicknesses. What is the relative? Generally, supposing in the earlier example I had given, supposing if it is a pipe material, metallic pipe material, lagged with outside by some insulation. Supposing if this white color arrow is indicating pipe material, metallic pipe, and this is the insulation lagged around that metallic pipe. Definitely, if this, say for example, like this is steel, this is say for example asbestos, which resistance will be more? Easily we can decide that resistance offered by the asbestos, which is an insulating material, will be far greater than the resistance offered by the metallic pipe. Metals are very good conductors, they cannot offer good resistance, because when the conductivity is more, resistance will be lesser. Okay, obviously insulating materials will be offering you great resistance as compared to the metals. Okay, so by seeing the materials itself, just by reading the materials itself, you would be able to understand, you will be able to estimate whether the resistance would be able to resistance will be more or lesser. If you are given three materials, just by reading the conductivities, we can easily make out which resistance will be greater. Okay, and moreover, in the case of the in case of cylinders, if length is not given, if length not given in cylinder, in length of cylinder not given, in the problems, I mean to say, if the length of cylinder not given, then calculate heat transfer rate per unit length. In the gate problems also, heat transfer rate per unit length. That is L is equal to 1 meter. Right. Now, okay, we have seen this composite cylinder. Now, I will consider the most general case of the radial conduction heat transfer in cylinders. Most general case in the sense, there is some metallic pipe. There is some metallic pipe. Inside, some combustion of the fuel is happening. Inside, hollow metallic pipe is there. Hollow metallic pipe. Inside that hollow metallic cylinder, there may be some combustion of the fuel is happening. Some fuel is burning, and that metallic pipe is lagged with some insulation, maybe some asbestos or glass wool or refractory brick, and outside the brick will always have the atmospheric odor fluid. So, we have a hollow pipe, inside there is some fuel is burning or steam is condensing, whatever it is. That means there is some heat generation happening, and that pipe is lagged with insulation, and outside the insulation you have the atmospheric air. So, that general case of inside convection will be there, outside convection will be there, in between there will be a conductions through the composite cylinder. So, it is a conduction convection heat transfer through a hollow composite cylinder. That is a very generalized case. Radial conduction heat transfer . Radial conduction heat transfer. Radial conduction convection heat transfer, more correctly, because convection also is there. Radial conduction convection heat transfer through a hollow composite cylinder. Hot gases are there, some combustion gases at Tg. This is the outside solid material, maybe insulating material, having a thermal conductivity K2. Inside material thermal conductivity is K1. Okay. There is a colder ambient fluid. Colder ambient fluid, maybe atmospheric air. So, there is a radial heat transfer happening between the hot gases and the ambient air. This is the radial heat transfer happening between the hot gases and the outside ambient colder fluid. L is the length of the cylinder. Okay, just by viewing the figure, you should be able to understand in what way the heat transfer may be happening. Okay, I told you earlier also, whenever you are reading a gate question paper, just try to make out the problem, try to reduce the problem to a small figure, make out a small figure. So that will give you a complete idea. Transfer that problem into a small figure, and whatever the data given, try to mark in the figure and try to analyze. So that way things becomes very easy. Okay, you can easily understand the problem clearly if you just transform that problem into a small figure like that. I think you should be able to understand this figure there. There is a hollow composite cylinder. Inside there is a combustion gases are burning here, generating heat, and those gases are at a temperature of Tg, and outside colder ambient fluid is there at T infinity. So Tg is much greater than the T infinity, therefore a heat transfer is happening. What is the mode of heat transfer here? What is the mode of heat transfer between the hot gases and the inside surface? What is the mode of heat transfer? Convection. Whenever we are talking about the convection mode, what is that coefficient? That must always be given H, the convection heat transfer coefficient. So convection with H1. H1 is the inside convection heat transfer coefficient. I would like to write it here. H1 is inside convection heat transfer coefficient. The other name is film heat transfer coefficient. H has got two names, convection heat transfer coefficient or film heat transfer coefficient. Inside convection heat transfer coefficient. So the mode of heat transfer here is convection between the gases and the inside surface. Let me mark the radii also, then you will understand. This is the radii R1, this is the radii, junction radii is R2, and this radius is R3, outer radius, outermost radius, innermost radius in R1, outermost radius R3, and the junction radius is R2. And first heat gets convected here, then heat gets conducted, then conducted, and here what is the mode of heat transfer from the outside surface to the colder ambient air? This is a colder ambient air at T infinity. This is again convection. Whenever we talk about the convection, that should be associated by the convection heat transfer coefficient. You speak of convection, H will be there. That H2 is the outside convection heat transfer coefficient. Units watt per meter square Kelvin. HV units are watt per meter square Kelvin. K units are watt per meter Kelvin. K is a property but H is not. So this is the rate of radial conduction heat transfer. Look at this yellow arrows there. This will indicate the rate of radial conduction heat transfer between the gases and the ambient air. Assume steady state. Assume steady state, one-dimensional, assume steady state one-dimensional heat transfer between hot gases and ambient. Between hot gases and ambient air. So now how many resistances you may expect between the gases and the ambient air? How many resistances you may expect? There will be 4 resistances. Convection, look at this. There is a convection here, convection, conduction, conduction, and outside again here and again outside here there is a convection. Convection, conduction, conduction, and again convection. Totally there will be 4 resistances against the heat flow between the gases, radial heat transfer between the between the gases and the ambient there is a radial heat transfer. In total there will be 4 resistances, convection, conduction, conduction, and again outside. This is again outside, it is convection. Okay. So the mode of heat transfer occurring between a solid surface and the surrounding fluid will be convection. So there are 4 resistances. So the thermal circuit comprises convection, conduction, conduction, and again convection. This is Tg, this is T infinity. First resistance will be convection, right? 1 upon, what is the convection resistance formula? 1 upon HA. What is the area of contact inside? 2 pi R1L. Mind that earlier also had given you that convection resistance is given by 1 upon HA. What is that A? Area of contact between the fluid and the solid. What is the area of contact between the fluid and the solid at the inside surface? Look at this, 2 pi R1 into L. This is the convection happening here. This arrow indicates convection. The area of contact between the gases and the inside surface is 2 pi R1 into L. That is this 1 upon HA. The first resistance is the convection resistance. Followed by there is a conduction resistance here. This is conduction resistance offered by the inner material, pipe material, that is ln R2 by R1 divided by 2 pi K1L. And again followed by there is a conduction resistance offered by the outer pipe material ln R3 by R2 divided by 2 pi K2L. And finally we have the outermost, outside there is a convection, 1 upon H2 into 2 pi R3L. Look at this one. What is the contact area at the outermost surface? At the outermost surface, the contact area is 2 pi R3 into L. The area of touch, area of exposure between the outermost surface and the air will be 2 pi R3 into L. The flowing current is Q. The rate of radial heat transfer is Q. Flowing current is Q. Now these terminals also I would like to mark. These terminals are marked as, look at this, this is T1 here at this surface, this is T1, innermost surface. Junction temperature may be T2, this junction temperature is T2. The outside surface temperature may be T3 here. At R is equal to R1, T is T1. At R is equal to R3, this temperature may be T3 here. Okay. The T3 is here, the outermost surface temperature, that is T3. Innermost surface temperature is T1. This is T1. This is. At R is equal to R1, this is T1. At R is equal to R3, T is equal to T3. So T1, T2 and T3. What is T2? At R is equal to R2. This junction temperature can be thought of as a T2. Try to understand the thermal circuits and the terminals. It's very important to just to understand the thermal circuit and the terminals of the terminals, resistances existing, what is the current, what is the values of the resistances, what are the terminals corresponding to the temperatures here. So Tg is the inside temperature, that is a first terminal is the temperature of the gases. T1 is this temperature, T2 is junction, T3 is the outermost surface, T infinity is the outside fluid. I already said this symbol T infinity is usually given for the ambient temperature or the surrounding fluid temperature. So the rate of radial heat transfer between the gases and the outside ambient will be Tg minus T infinity divided by sum of all the resistances, that is 1 upon This is the Q is the rate of radial heat transfer. This is the rate of radial heat transfer between hot gases and ambient. So, which resistance will be more, which resistance will be lesser, it all depends upon the what is the H value. Supposing if there is a hot water, so I am just giving an example. Supposing if it is instead of gases, there is a hot water. What is the H values associated with water? Will be definitely much more than with the gases. So, when H is more, this resistance will be lesser. Suppose if there is a hot water, very hot water flowing inside, the H values associated with the water will be much more flowing water, then this resistance will be obviously lesser. Supposing outside the fluid is atmospheric air, with air the H values associated here, outside convection, it will be lesser. I have given the approximate ranges of H also. The H values observed with the gases will be quite lesser as compared to the H values observed with the liquids. So, you can have an approximate estimation or approximate idea, relative idea about which resistance will be more, which resistance will be lesser. Supposing if this is the metallic pipe material, definitely this resistance will be lesser. If it is an insulating material like asbestos or the glass wool, definitely that will offer more thermal resistance because K is low. For the insulating material, K is low. It is expected to offer more thermal resistance. Right. So, this is the formula, a generalized case where you have taken the convection inside, convection outside, we have the conductions in between, all are in series because heat current is flowing one after another, first convection, conduction, conduction and again by convection. So, whenever there is a multi-mode heat transfer is there like this, it is always customary, our common practice, it is always customary or common practice to bring in one important coefficient called as the overall heat transfer coefficient. Earlier also I defined that for the slabs. Now here also we define because we have a multi-mode heat transfer, inside convection, outside convection and in between conductions are there. So we will bring in that, we will define that overall heat transfer coefficient. But here in this case of the cylinder, we will get two different overall heat transfer coefficients. One based on the inside convection area and the other based on the outside convection area. We will define two different overall heat transfer coefficients, one based on the inside convection area, that is at the inside surface, the other based on the outside convection heat transfer area. Okay. U is always defined based on the convection area only. The reason is the units of U and the units of H convection coefficients are equal. The units of U and the units of H are same, watt per meter square Kelvin. I will define two different overall heat transfer coefficients, one based on the inside area, convection area and the other based on the outside convection heat transfer area. Defining overall heat transfer coefficient UI, that is based on inside convection heat transfer area and from the equation rate of radial heat transfer Q is equal to UI AI delta T. AI is the inside convection area, which is equal to UO AO delta T, where Q is equal to AI is the inside convection area, that is 2 pi R1L. What is the delta T? The total thermal potential in the entire circuit. Whenever we define the overall heat transfer coefficient, the delta T should be taken as the total temperature difference. What is the significance of U? It takes into account all the thermal resistances existing in the circuit, thermal circuit. It will take into effect the entire effect of all the resistances put together. I mean, if the U value is more, the total thermal resistance against the heat flow will be lesser. That is the significant thing, important thing you should understand. If U is more, the total thermal resistance against the heat flow will be relatively lesser. So, why I need to define two overall heat transfer coefficients here is, we have a different convection area here and we have a different convection area outside. In case of the slabs, there was no such need, because in slabs, both sides of the slab are having the same convection area. So, it was sufficient to just define only one U. Here it is not like that. Comparing, see, if you just call this equation as 1, and this equation as 2, comparing 1 and 2, we get the expressions for UI and UO. Comparing 1 and 2, we get 1 by UI is equal to similarly, you just look at this. When you are writing based upon the UI, you are getting the R1. Here. When you write based upon the outside convection area, if you write the based upon the outside convection area, similarly, if you write it based on the outside convection area, you will get in the numerator, you will get the R3. How did you get this? Very simple, just to multiply numerator and denominator with, say, for example, if you want to get UI, multiply numerator with 2 pi R1L, denominator also 2 pi R1L. Compare with this equation 2. Compare with that equation 2, you will get the, this is a Q, the total heat transfer rate. Total radial heat transfer rate is Q. Comparing 1 and 2, we get these two expressions for the overall heat transfer coefficients based upon the, one is based upon the inner convection area and the other based upon the outside convection heat transfer area. This U is a very important term. Particularly when you do the heat exchanger analysis in both LMTD method and effectiveness NTU method. In almost every problem of heat exchanger, we are supposed to use the overall heat transfer coefficient value, which is given obviously in the problem of the heat exchangers. Right. Now, what are the units of U and units of H are same? That point I have mentioned earlier also. What is the significance of U? U signifies how much total thermal resistance will be there relatively against the heat flow. The physical significance of U is that if U is more, the total thermal resistance against the heat flow will be lesser, therefore heat transfer rate will be more. Overall heat transfer coefficient. Overall means every resistance against the heat flow are put into effect, are taken into account. Right. Now, having seen the very important thing of overall heat transfer coefficient and the radial convection conduction situation, now I would like to apply this particular radial conduction convection heat transfer concept to a very important topic in the conduction chapter called as the critical radius of insulation. That topic was asked many times in the GATE. There were so many questions asked in the earlier GATE examinations regarding that particular concept called as the critical radius of insulation. Okay.